screen space, pixelation, and palletization effects. Basically a way to make something based on more modern graphics have an imitation retro look. To try and make something like this, or this, or this, or this, look a little bit more like something like this, or this, or this. Now there are some definite limitations. You're not going to completely imitate the effects or the appearance of something made in, say, the 90s using pixel graphics unless you're using real sprites, but the idea is to get as close as we can. So, here we have a complete screen space shader that takes care of the whole thing. It is divided into two main parts, the pixelator, and over here we have discrete LUT, lookup table. It's a color lookup table that will replace the colors with those that are most similar within a smaller palette. So we'll start with the pixelator. The pixelator is the simpler of the two by far, takes much the least work. So we bring in the screen UVs. In other words, the X and Y coordinates on the screen. We have to split those. We have to multiply them by the resolution on each axis. So red or X or U gets multiplied by width. And then G, which is the Y or the V, if you think of it as a UV, gets multiplied by the height. Then we apply a floor effect, which will bring everything down to the integer right before the number. So if you have, like, you've multiplied it and you have 3.5, it's going to turn it to 3. And then after that we add 1/2 and then divide it back by this, because this needs to be on a scale of 1 to 0. So we're multiplying it to the full size of the pixels. We're using the floor to split it into individual pixels. We're using this 0.5 to move it to the middle of each pixel, each of the pixels we're creating, to sample the real pixel in the middle of our fake pixel, you could say. And then we're dividing it back down to create a UV that will translate everything within our larger fake pixel. Every pixel within that, every real pixel, will be the same color as that one. And the default sizes I picked, by the way, for use with the pixelator are 384 by 216. And the reason I'm picking that is a lot of early 90s games used 320 by 200, which was a 4 by 3 aspect ratio. Modern monitors use a 16 by 9, and that's about as close as you can get by a 16 by 9, and it also divides evenly. So each of the pixels on a 180p monitor will be 5 real pixels by 5 real pixels, and then higher resolution monitors, if you get into all the 4K and so on, are usually multiples of the 180p. So that way we have nice even pixels. So that's fairly simple. And if we go here, let's put in a nice picture of my dog. And we can maximize this, and there are no effects right now, and behind him is a devlog of a game I was working on recently. But if we go here to our graphic settings and turn on the pixelation, it's fairly subtle, but if you look, there is more pixelation than there was. You can kind of see where the pixelation is. Now, it's fairly subtle by itself because we're still using the 16 million plus colors from a full RGBA palette. Full RGBA, so you're getting all the color variations. You have to look close to see where the pixels are with the pixelator alone. You can, of course, make the pixelation more obvious if you go to the material, that represents the pixelation, and change the resolution, and there you go. Much more obviously pixelated. But moving on to the color substitution, that's what we need to talk about now, because that's what will really make it look like something from an old game. So what we need to do is take all the colors and compress them down into a smaller palette of, say, 256 colors, which would be typical for a game of the earlier mid-90s. Because there were technical limitations, that was about how many colors you could have at that point in time. So basically, we want to take something like this, and if you're wondering, this is the color palette from the game Hexen Beyond Heretic from 1995, not 85, 1995, but these are the colors used by the game Hexen Beyond Heretic. And we want to change this into something like this. This is a color lookup table, or LUT for short. And with each of these squares, you have red on the horizontal axis and green on the vertical axis. So each of these squares is 64 by 64. In theory, you could make them bigger, but this is a fairly standard size. And then each of these squares, as you go along, represents one more level of blue. So this is maximum blue, this is no blue. And by having this, you can take the pixels, read them in a shader, and turn them into numbers to look them up as coordinates on this table to convert them to the colors you want. And these are the same colors as we saw back here, the same colors, the Hexen colors, but now they've been turned into this table. So you can look up a full RGB or AGBA color and find one of the colors from that particular game and substitute the pixels. This will find things by the closest distance, treating R, G, and B, the red, blue, and green, as position vectors, and find whichever points you basically think of that as, and transform it to whatever is closest. Now, there are some that will suggest doing this based on other color schemes, such as HSV, that's hue, saturation, value. I've experimented with that. A lot of the internet will tell you that's the way to go. My experience is that that produces terrible results. The further you get from a straightforward RGB, the worse it gets. So, how are we going to do that conversion? Because first, we need to create this table, and then, as a graphic, obviously, that can be loaded as a texture. And then we need to create the shader after we've done that. So going back over here, what we need to do is we need to take all the colors and compress them down into a smaller palette, something like 256 colors or less, because that's what was typical of the 90s, and we're really not going to go into the 16 colors and so on you'd have to deal with in the 80s. And for that, we'll need to look at some code. So we'll start with color extensions. And these are just some extension methods I added to color that are mostly in order for finding the distance and based on different color models. And what it'll do, it'll take the components of a color and treat them as coordinates. So the colors are treated like points in space, and how similar or different they are is equated to their distance. The further apart the distance, the more different the colors. And you can see I have some based on RGB, and also some based on HSV. I did this experiment HRGB where I added the hue on top of the red, blue, green. But these are then used with the color registrar. And what the color registrar does is it registers colors to this list. you can put in a color, and if the color is not already in the list, it will add it. You can also give it a texture, and it'll go through the texture one pixel at a time, and if the color of that pixel is not in the list, it'll add it. So you can use a texture that represents the palette you're trying to put in, and it will convert it into a list of colors. And then it has some methods to find the closest color to one that's put in. So you put in a color, and it finds a color in the list that is most similar, that is closest by distance to the color you sent in, and returns the color from the list. And you can do it based on RGB or HSV, also the HRGB, and there's just a hybrid method that considers both RGB and HSV different distance. And again, my experience playing around with this and testing it was that RGB is the best. The further you get from a simple, straightforward RGB, the worse the results become. So with this color registrar, you can then go to generate LUT, and this is what actually will generate the LUT. It has a field for the palette, a field for the LUT, which will be the output. It has a color registrar that will read the colors from the palette into, and then it will also output some things about the format and the number of colors it found and the dimension and so on. But once it gets going, it will go through each color in the RGB. It'll just iterate, R, and then iterate as an outer loop, and then G is the middle loop, and B is the most inner loop, and every possible color combination. And it will write that color into the palette in the correct place, but only after feeding it through the color registrar to get so that it converts it to one of the colors on the list. And that way you get a table out that maps all the colors based on what they're closest to as a texture. And if we go back over to Unity, so to demonstrate this, first I'm going to turn this video off because you don't want this playing while we're doing it. Then go over to materials, and this that I have here, I'm going to replace it with this LUT 64. Now the created LUTs I put over here, but where they are created, it uses this. So we have that, and to create a new LUT we need a palette. So I'm going to use this one here, which came from Grant Abbott from a course he did on Game Dev TV. But I'm going to use that, and I'm going to generate a LUT based on this palette right here. And I hit play. Hold on. And then there we go. And it's generating a LUT that will convert colors to colors found in this. And because there aren't very many colors, it's not a long search through the list, so it goes by pretty quickly. And stop. And no, I don't have a proper editor tool. It is running essentially as though it were a game. One thing that's important to note is you do need to have read-write on both the image you're reading and on the LUT you're outputting it to. Otherwise, you will get an error and it won't work. So that's how we would go about creating a LUT. And let's just make it look pretty again by putting my dog back. But there is a newly generated LUT. So what do we do with the LUT? Well, it's actually easier to show it as code first, and then we can go back over to the shader graph. So if you go to this class here, Texture Draw, which I created with some utilities to manipulate textures, you have this Apply LUT. It will take in a texture, and it'll take in a LUT, which is, of course, they're both texture 2Ds. And this is all a C#. So to get the rows, you would basically take the cube root of the width of the texture, because it should be, that's just how it should, the math should work out. It should be something like, you know, a 64 by 64 and then a 64 height, which that 64 should itself be a square number. So you have 8 rows by 8 rows. So you get 8 rows, and then divide the total width, because the total width for these is 512, to get the block size, which is 64. And the color size is block size -1. For certain reasons why when it's searching. But then we can go through this image 1 pixel at a time for the X and the Y. And with each color, the colors are going to be here treated as 0 to 1. We're going to multiply that by the color size. So it's the same width, but it's -1, so it's 0 through 63. And that gets R, the G, and the B. And then for the B, you have to take the number of rows and get the remainder, the modulus or modulo, I've heard it called both. But get the remainder of dividing it by the rows, and also the result of dividing it by the rows, you know, as an integer, to get the row and column, and then multiply that by the block, by the full block size, so it can jump the full width of each of those blocks. So we can then look that up in the LUT texture and set the pixel in the original texture to what it can find in the LUT texture, looking it up with this XY. And then when it's done, apply. So that's the basic logic. You have to multiply in these ways. Multiply by this, and you have to use the modulus and division, and then some more multiplication to get that. And then converted to a shader graph subgraph. So then you have the color coming in. You're splitting off your R, your G, and your B. We're not using alpha because it's screen space, and we're completely replacing the original screen image with the new screen image. So you can take the B, and you have to do the modulo, and you have to do the divide by the number of rows in both cases. You have to use floor because shader graphs treat everything as floating point. There's no distinct integer, even you can tell it to be treated as an integer for input. In here, everything's treated floating point. So to make it treated as an integer, you have to add this floor. You have to multiply back in the table size. I mean, that is, if you go back over here, that is the equivalent of this multiply by block size. This and this, that's what we were looking at in shader graph form. We're also taking the red and the green then, and we're adding them back in. And then we're dividing by the actual LUT size to get things into the correct 1:1 UV to be combined. Saturate it to make sure everything is between a 0 and a 1, and then use this as a UV to look it up on the LUT texture as a texture sampler and output that. So when you go back to the whole thing over here, we've taken our original UV, we've pixelated, we've got the color, and the colors, and we've used this discrete LUT then to turn the pixels into a new UV to look up in this texture, but to get the color. And if you to see it all put together, let's go to settings, and you can see it with just, because I did this separately to see it, you can see it with just the color adjustment, but you can also see it with the color adjustment and the pixelation both applied. So we can maximize And there you go. Pixelated and in a color palette. In this case, specifically the color palette of the game Hexen. I actually did things for a bunch of different known games and systems just to try it out, as well as a couple color palettes of my own creation. But this is my dog, pixelated to an early 90s resolution and done in the color palette of Hexen Beyond Heretic. I have another scene up here. Now there is a little bit of a problem with some of this, and that for some reason, specifically, dark colors become darker and it often becomes difficult to see. And you get these things where you're only using the dark colors, so you're not using as many colors as you should. And what I've concluded you need to do about that is you can't be feeding it in something that's been already processed through realistic lighting, because that's already dimmed things a lot. If you think about games in the early 90s, Doom, Hexen, even horror games like the original Alone in the Dark, they're all actually have these fairly bright, vibrant colors, and that's really what you need when you have a small palette in order to make things look good. So if we go up here, I've taken a scene that from an asset pack I released, and I've modified it to use cartoon colors. So here we go, and if we hit play, this was originally realistic looking, but with the shader on it, you can see it looks very pixelated. Let's start this over and the sky's not that good, because if you were actually doing the whole thing as real pixel art, you'd probably use dithering and so on in the sky to make it look better. But let's play maximized. Again, we can walk through this. And I believe this is also Hexen's colors. Even though I did try things out using the palettes from Doom and colors from like the original NES and Atari. Now, one thing you do have to consider is when you get close to something, the pixels in the graphic may be smaller than the pixels of the screen resolution. An extreme example would be something like a 32 by 64 imp that takes up half of a 320 by 200 screen. So it's like 160 pixels are showing 32 pixels of the imp. If you're playing Doom, you know what I'm talking about. That's something you really can't change. Handle this way very well. You could make the texture lower resolution, but the outline is still going to be based on the 3D model. But for these walls, I actually made the point of changing their resolution, so when you get close, they have really big pixels. A resolution more similar to a game from that era. So if you go in here, you can fly around, and things look fairly 90s. It's not exactly the way like a real game from that era would have looked, but it's pretty good. It's pretty close. Over here, this is, I'd say, the most interesting room, and you can fly around, and you can with this, and you can look at these different graphics, and it actually looks kind of like a scene. Yeah, I kind of messed up where the way the chairs are placed, but oh well. And everything looks very much like you might expect from an old game. So I'll call that a success. It's not perfect, but it basically works. It looks kind of like you would expect from an old game. So again, though, after doing all that, you still need bright color, something like an unlit or toon shaded models and materials if you really want it to work in anything other than very well lit bright areas. And well, that's kind of how games looked like back then anyway. So anyway, I hope you found this interesting and maybe informative. Have a great day.